Hello everyone. My name is Tyler, and I'm here to talk about our paper, the application of Learnable STRF Kernels to the 2021 Fewer Steps Challenge Phase SAD Challenge. And yeah, this work was done with Yangyang and Richard Stern, all from Carnegie Mellon University. So first is a brief overview of what the actual Fewer Steps Challenge is. So it's organized by the University of Texas at Dallas Center for Robust Speech Systems, and the entire FSC data contains around 19,000 hours of naturalistic speech sampled at 8 kilohertz from the NASA Apollo missions. So you can imagine it's very noisy, tons of channel variations and other degradations. And the challenge consisted of multiple speech-related tasks like ASR, speaker ID, but we focus on just the speech activity detection task. So here are just the summary of the key findings that we found to improve robust SAD performance. So the first one, which I think is very common now, but convolutional current neural network architectures strongly outperform like classical signal processing based methods and the SAD tasks, and that's pretty common now. And secondly, including modulation domain information by utilizing spectro-temporal receptive fields improves robustness to additive noise. And last but definitely not least, using SpecAugment during training is very beneficial for improving generalization capabilities. I think it's been used a lot in ASR, and we found that it actually helps a lot for speech activity detection as well. So here's an overview of our system that we submitted to the Fewer Steps Challenge. It's a pretty standard CRNN system. It contains convolutional layers, and then following the convolutional layers are recurrent blocks, and recurrent blocks, and after the recurrent blocks, an MLP makes a prediction of speech activity for every 40 millisecond frame. But the main difference between our network and a standard CRNN network is the first layer, which will be the main focus in this talk. So rather than just using unconstrained 2D convolutional kernels in the first layer, we actually use the standard COM2D layers as well as STRF kernels in the first layer. So the slight modification is just what kind of kernels we use in the first layer. So what are STRFs, or spectro-temporal receptive fields? So STRFs are motivated by physiological structures that are believed to exist in the central auditory system. And each kernel responds to a range of temporal modulation and spectral modulation patterns. And you can sort of think of the kernels as a bank of 2D modulation selective filters. So rather than a standard 5x5 kernel, where the frequency response of the kernels is not tuned to any specific temporal or spectral modulation, these kernels are tuned to very specific temporal and spectral modulation because each of the STRF kernels are parameterized by a rate parameter and a scale parameter, that sort of control the temporal and spectral modulation selectivity respectively. So the question is, why do we even use STRFs? So we use STRFs because we can sort of obtain the spectro-temporal modulation domain by getting a bank of 2D STRFs, where each STRF is individually tuned to a very specific modulation pattern. And if you convolve it with the input representation, then you sort of obtain this modulation domain. And now that we have this modulation domain, you could pass it to a neural network, and now the neural network is learning speech activity from the modulation domain rather than the standard time frequency domain. And the reason why we use this modulation domain input is because it's sort of well studied that speech and noise are a lot more separable in this spectral temporal modulation domain due to the unique modulation characteristics of the two. So it's well studied that speech has very specific, it's concentrated at low temporal modulations around the 2 to 8 hertz range, and there's a lot of work that shows that low modulation is also good for intelligibility and other speech-related tasks, and also for extracting robust features, looking at low spectral modulations is also a very common thing. You can imagine the MFCC calculation where you use the first 13 order coefficients is sort of just analyzing the slow temporal modulations. And then we also use STRFs because it has been successfully applied to speech activity detection, but they do it quite different, and we'll explain that later. So that previous work that used these STRFs to extract more robust features is sort of what motivated this work. And there's many different implementations of STRFs. Some are more complicated than others. For this implementation, we used the Gabor-based STRF, which is basically just multiplication of a complex sinusoid and a Hanning window. So you can imagine these STRFs are these 2D kernels, but in the traditional neural network sense, I guess, rather than learning all 25 weights of a 5x5 kernel, you're just learning these 2 parameters, the rates and scales that control the modulation. But there is one major issue. So the one major issue is that these STRFs are 2D kernels that are parameterized by 2 continuous values that leads to an infinite number of possible kernels. So previous work, they mathematically define these STRF kernels, but they want to know, they can't possibly use all the different STRF kernels. So they heuristically found what are the best set of 60 or so STRF kernels. And once they heuristically found which STRF kernels were the best, then they used that for all speech-related tasks. But that was done a while ago. But now that we have deep learning and neural networks, rather than just choosing beforehand which 60 kernels to use for every single task in the future, we just parameterize the first layer of a neural network to be these STRF kernels, and now the neural network is just adapting the rates and scales parameters for the specific tasks, so you don't have to choose the parameters beforehand. And this idea has been applied to voice type discrimination, and so we actually found that if you only use these modulation kernels, you actually don't get superior voice activity detection performance. And we believe that these STRF kernels are actually analyzing medium time patterns. So the temporal resolution is actually pretty poor since they span around 300 milliseconds. And for voice activity detection, you need a lot better temporal resolution than 300 milliseconds. So we actually found that if we include just the regular standard convolutional layers, typically 3x3 or 5x5, but if you add that to the STRF kernels, then you actually get a lot better performance. And prior work that used these STRF kernels, they had to do some sort of dimensionality reduction. Because you can imagine that your backend classifier typically takes in some time frequency representation, but now that you have all these STRF kernels, now the dimensionality is now time, frequency, rate, and scale. So prior work, they will apply dimensionality reduction to get small amount of features, and then they pass that to the backend classifier. But now, rather than doing this preset dimensionality reduction, we just pass it on to the neural network, and it does it by itself, I guess. And so here's just a brief summary of constrained STRFs and unconstrained 2D kernels. So the learned STRF kernels are more interpretable. You can actually see what rates and scales it picks up. And for each kernel, there's only 2 learnable parameters. So if you're sort of constrained on size, then this one has 2 parameters. And this is sort of constraining the rest of the network to operate in the modulation domain. So you're sort of placing this prior on the neural network, and then the learned kernels are not, the unconstrained kernels are not as interpretable, because if you plot the frequency response, sometimes it's hard to tell what they're actually picking up. And depending on how big the kernels are, you have more learnable parameters, and then the neural network with these unconstrained kernels are free to pick up any cues from the input representation. So here's the experimental setup of the challenge. So we actually only trained with the 63 hours of labeled data that was provided for the challenge. I think, the challenge was an open data set, but we only trained on the 63 hours and didn't use any external data sets. And then, evaluation was done on a blind test set that had, different channels, and also an unseen Apollo 13 mission. And this data set is challenging due to the channel variability, and there's also varying SNRs throughout each recording, and also the lower sampling rate. And also for evaluation, we didn't apply any post-processing, so the neural network outputted a probability score for every 40 milliseconds, and we simply just used a 0.5 threshold for a speech or non-speech decision. And we also wanted to evaluate robustness to additive noise. Since this data set was fixed, we actually did some more experiments where we added additional noise to the development set just to see the robustness between the STRFs and the standard kernels. As said before, the primary metric for this challenge is a decision cost function, which is basically a weighted average between the false negatives or misses and false positives or false alarms. So this is just an example of DCF curve. So you can see that the DCF depends on the threshold you choose. So sometimes you might need to find the optimal threshold because that could really that could really change what DCF you get. But in all of our experience, we just used 0.5 since it seemed to work well. So here's the first result. So the first result we found that's very similar to a lot of other results in the field, that SpecAug consistently improves speech activity performance on the development set. So we have our baseline, which is the C and RNN baseline, and our hybrid STRFnet on both the developments, or on the development set. You see there's a big difference between when we use SpecAug and when we don't use SpecAug. And I think that's very consistent with prior research in ASR and other fields. And so this experiment, we wanted to evaluate, well, how well does this do when we add noise? Since we know that there's probably a very finite set of noise in these space missions, we added noise from the DNS challenge. And yeah, these noise types are a lot different than the noise that's seen in the field of steps. And we found that, yeah, across all signal-to-noise ratios, that our hybrid STRFnet outperformed our baseline CNN. And yeah. And because we have STRF kernels in the first layer, we can actually plot the rates and scales distributions to sort of see what rates and scales are the kernels actually converging to. And on the top, you can see the rates distribution. And it's nice to see that for rates, a lot of the kernels converge to around 4 to 5 hertz, which is also aligns with like the syllabic rate of speech. And there's a lot of research that's shown that if you analyze temporal modulations, you can even just bandpass filter the signal around the 2 to 8 hertz range, and you can actually get a more robust representation since speech is highly concentrated around slow temporal modulations. And it was nice to see that the STRF kernels also converge to something similar. And if you look at the scales, so that's the spectral modulation, a lot of the STRF kernels converge to the slower spectral modulation, which is consistent with, or which is similar to what MFCCs are doing, where you do a frequency analysis on a log-model spectra, and you take the first couple coefficients which correspond to slow temporal modulations, which is very similar to what these STRFs learn to pick up as well. And yeah, and here are the final challenge results. So as you see that our baseline system outperformed the second place team as well as the challenge baseline. So it actually made it kind of hard because yeah, when you have a baseline that's already won, it's kind of hard to beat. But we found that our hybrid STRFnet gives very modest improvements over our baseline. But as shown in the previous slides, that once you evaluate on even more unseen noise types, then you see this performance gap with the STRF kernels. And yeah, the only difference between our baseline and the STRF is the first layer, and the number of kernels are always the same. So here are our final conclusions. We combine generic unconstrained 2D kernels in the first layer of a CNN with learnable STRF kernels, and the hybrid STRFnet system consistently outperformed a competitive baseline that uses only generic unconstrained kernels. And a very important result that we got is SpecAug is essential for improving generalization capabilities. So for future work, we recognize that speech activity detection is usually sort of the initial stage of a system, probably on the edge. So it would be more beneficial to develop a real-time speech activity system. And we're hoping that since we're injecting this prior knowledge about modulation and the robustness to noise and speech, maybe this will allow us to build smaller systems because of this prior knowledge of modulation. And the second future work we're going in is to design a learnable front end that is more suitable input representation to STRFs. So learnable front ends are a very popular thing now. And right now we're just using log-model spectra since that's what everyone uses, and that's what's used in prior research for STRFs. But that might not be the most optimal representation for STRFs. Maybe there are different center frequencies that are more important for these kernels, and also different bandwidths that are more important for these kernels. So we're working on combining learnable front end with a learnable, 2D layer. Yeah, and thanks for hosting the challenge, and InterSpeech for also hosting this. That's it.
Thank you. Any questions from the audience?
Hi, thanks for the talk. But yeah, you mentioned that the STRF kernels, as they stand, they capture like a low frequency resolution, or It's like a middling band resolution, something like
Yeah,
that?
so they're picking up very specific. So you can imagine that you have a time frequency representation, but if you do another 2D Fourier transform on a spectrogram, then now you're sort of analyzing the spectro-temporal frequencies in your 2Ds, in your spectrogram. So you imagine it's like another Fourier transform on the spectrogram. But the difference between that is we're using STRF kernels that are more localized, so it's not a 2D Fourier transform across the whole spectrogram. It's just like in local patches, since speech is pretty stationary or non-stationary.
Yeah, and I saw in those learned CNN kernels, it's like there's a lot of them where it was like just noise, it seemed, and other ones it was just
Like the
just
actual.
a big blob. So do you have any idea of like which ones capture more high frequency versus low frequency content of the?
Wait, you mean the
I guess
distribution or the actual kernels themselves?
Yeah, I was looking at the plots of the kernels that you had.
Oh.
Yeah, it was in one of the block diagrams.
Well, you can sort of directly see, like the fast ones are capturing, like, so since these kernels are being convolved with the input representation, so the ones that are fast, I guess horizontally, that's analyzing fast temporal modulations, and the ones that are going up and down, those are analyzing fast spectral modulations. But these are STRFs, so they actually model the joint spectro-temporal modulation. So I guess the ones you see here, yeah, a lot of them are kind of fast, and then the one in the middle is analyzing very slow temporal modulations.
Any other questions? I have a question related to that. So the STRF kernels were learnable, right? You let them,
Yeah.
from the initialized version, you let them update.
Yeah.
Did you try to visualize them, or those that you're showing here are the initial ones or the learned ones?
Those are the learned ones, but there's like
Are they
60
very
of them.
different? Are they very different from?
Oh
the
yeah, so
initial?
they do change. So they're actually initialized. Let's see. Yeah, so the kernels are actually initialized uniformly, and then you see that they all sort of converge to lower modulations for both spectral and temporal, but more so for the temporal modulations.
Thank you.
Yeah.
So I will maybe ask another question. If you're looking at only noise or random type conditions, what does the output of the kernels look like with just speech versus noise?
I see. Well, so yeah, I guess we didn't. That's probably the next steps to sort of analyze what they actually look like with noise. But when let's see.
It's following up on your question, because if you have long periods of silence or noise, you would expect that the output from the kernels are going to look very different.
Yeah, the output for noise is probably a lot more random than speech. So speech is probably a lot more structured. And for example, the spectral modulations, they probably capture the harmonics or the formats in the speech. So it's definitely a lot more structured for speech. But we don't expect the initial representation to be that separable. And that's why we have, I guess, the rest of the neural network to do the separation.
Okay. I'm asking that because there are 5 channels that were selected for the challenge, but each channel has actually very specific types of peculiarities because of how things are looped. So, thank you.
Okay, thanks.
Any other questions? I know you thanked UTD, but I would also put credit to NIST, Sajati, who oversaw a lot of the logistics for the challenge, and also Chris Seri from LDC. The two of them really worked tirelessly to make sure that the process was evaluated effectively.
Yeah.
Great job. And you finished first in the challenge.
Oh, yeah.
Yes.
We did.
So if you're around during the closing ceremony, you are being recognized there.
Oh, nice. I'll be around.
Any other questions from folks? We're looking online to see if there's any online, but we don't see questions there. Okay, let's thank the speaker again. Appreciate it.
Thank you.